Okay, I think we're just about ready to get started. Just wanted to make sure, welcome everybody to class. Seems like we're getting smaller and smaller with more and more people online, which is totally understandable given the current situation of everything. I wanted to make sure that everybody accessed lecture 4. I posted it on Canvas, but not very far in advance of class. I'm sorry, I posted the announcement on Canvas that the lecture 4 is updated in the repo. So just wanted to make sure, did everybody get that? Because I think it'll be good for you to code along on your own as we go through today. Everybody good? Anybody have any issues? Okay, so everybody has this with them. Okay, great. Well, then let's get started. Today we're going to be talking about a brief introduction to statistics. You know, this course is a kind of a mix of a lot of things. So we're going to try to get as much as we can out of statistics in a couple of lectures. So today we're going to talk about variable types, some ways to do descriptive statistics in Python, like finding the min, max, mean, median, standard deviation, a lot of those descriptive statistics that you've probably seen before. We'll look at some basic plotting functionalities, correlation versus causation, confounding variables, and then we'll talk a little bit about the difference between descriptive and inferential statistics. We'll be getting into that in more detail later in the class. And also we'll go over the difference between discrete and continuous random variables and talk about some of the most famous ones that we'll be using in this course, Bernoulli, binomial, and normal. Okay, so let's get started. So I like to think of variables as coming in 2 flavors. Now you can get more granular than this, but I kind of like to keep it simple. You can have categorical variables, or you can have quantitative variables. So categorical variables record a category. Think gender, color, true, false, education level, but could also be like Likert scales, you know, on a scale of 1 to 5, how much pain are you in, something like that. That would also be categorical. On the other hand, a quantitative variable records a numerical measurement. Okay, and so categorical variables might or might not have an order associated with the categories, you know, like average, good, excellent. You have an order there. And they may or may not have that order. But with quantitative variables, there's always an order because you're measuring something numerical. Quantitative variables, however, do come in 2 different types. We can have discrete variables. A discrete variable takes on a discrete set of possible values. So for example, what year were you born? How many teeth do you have? Any kind of count is going to be a discrete variable. A continuous variable, on the other hand, would be values that can be real numbers. And so think length, temperature, time. You can get any value on a continuum of values. Okay, so let's look at a couple examples and let's think about, are these categorical, quantitative discrete, or quantitative continuous? How about latitude? What do you think? Yes, I would say quantitative continuous. But this gets, there's a difference between what the variable actually is and how it's recorded. In practice, it may be recorded up to some numerical precision, like you're only getting 2 decimal places. And then at that point, you might argue, well, what we're really seeing is discrete. But as a variable, I'd say continuous. What about Olympic 50-meter race times? Yeah, I think kind of the same reasoning applies there as latitude. It is a continuous variable. Of course, we're limited by our ability to measure things, so it might appear discrete, but I would call that continuous. How about Olympic floor gymnastics score? Quantitative discrete? Does it, let's go back up to our definition, does it record a numerical measurement?
Yes,
this one is tricky. This is a little tricky because they use numbers like, the gymnast does their performance and then the judge holds up the whatever, 1, 2, 3, up through 10. It feels quantitative, but it's really not, right? It's like they're giving a category, an ordered category, but it's really not a quantitative measurement. It's somewhat of a subjective evaluation. I'm seeing some, but yeah. So actually the gymnastics score is actually a categorical variable. In some situations, categorical variables like that might be analyzed as a discrete quantitative, but still it's important to kind of understand that it's not arising from a numerical measurement. Okay, college major. Yay, an easy one. Number of offspring of a rat. Yes. Very good. Okay. All right, so today we're going to be focusing on descriptive statistics for quantitative variables. If we have time, we'll do a little bit about categorical at the end, but mainly we're going to be focusing on quantitative variables today. And we'll be thinking about how do we describe a data set with some summary statistics. So let's say we're given a data set, a sample, x1 through xn, of numerical values. So some descriptive statistics that we could compute for that sample, for that data set, would be, we could find the minimum value, we could find the maximum value, the median value, we could find the mean, right? Add up all the values and divide by the total number of objects. Okay, so let's see how we can do this in Python. We are going to be using NumPy for a lot of what we're doing today. So first thing, we're going to import the NumPy package as NP, like last time. This NP will be our little shorthand for NumPy, so we don't have to type out NumPy over and over again. And we're also going to be importing the pandas library. So we'll talk more about that next week, but we'll use it a little bit today to import data. And we'll import that as PD. And then one other thing that we're going to be getting our, learning how to do today, I guess I should say, is how to make basic plots. And so this plotting package is really helpful. So we're going to import matplotlib.pyplot as PLT, and we'll be doing that a lot in this course. And then this is setting a couple of defaults for that plotting package, like how big to make the figures and what style to use for the plots. Okay, so I'm just going to evaluate that. So you guys can all run that as you're going along. So make sure that you have everything imported. So let's look at some data. Our first data set we're going to look at is monthly average snowfall in Alta, October through April. So this is based off of data collected from 1980 to 2014. And you can check out the source there if you're curious. But for now, we're just going to make 2 lists in Python, right? Our first list is going to be a list of the different average snowfall values. And the second list is going to be a list of months corresponding to each of those values. So we see an average of 28.5 in October, 76.7 in November, etc. Okay, so if I ask Python, what type is that first vector, what do you think it's going to say? It's a list, very good. So it's a list, but then if I ask the type of the first element of the list, what is it going to say? A float, so we can check that, very good. So that thing is a list, the first element is a float. And if we do the same thing for that second list, we can see, months is also a list, but more specifically, if we look at the first element of months, we see it's a string, not a float. So we have a list of floats and a list of strings. Okay, and now for this example, we can count them and know how many there are, but when you have like a really, really big data set, you don't want to do that. So if we didn't know, we could ask the length of the vector and see that it's 7. So we have 7 months of data here. Okay, so then moving on to the descriptive statistics in NumPy, we can call this function, which is numpy.min, and it'll extract the minimum value of the vector. And I said vector because I'm from a math background, but array. And np.max will extract the maximum value. So let's see what we get. Yeah, minimum of 28.5 and a maximum of 99.66. Okay, now again, we might be interested in knowing in what month did this minimum occur, or in what month did this maximum occur? And for this example, we could just look and we could just see, well, okay, 28.5, that was in October. But again, if we had a really large data set, we wouldn't want to scan through all of the entries. We would want some kind of automatic way of extracting the index. And so for doing that, this argmin command is, or function, I guess I should say, is quite helpful. So this is not going to tell us it's going to tell us the index of the minimum value of the vector. So if we ask for that, then we can print that index and we can evaluate months on that index and also the snowfall on that index. So let's see what we get. Okay, the index of the minimum is 0. The months evaluated at that index is October. The snowfall evaluated at that index is 28.5. So that's just saying that the minimum occurs in October, which is the first element of the list. And similarly for the max, right? Okay, so we can also compute the mean with np.mean. Let's take a look at that. Okay, so we have a mean of 80.4 inches of snow. Sounds like a lot to me. I guess Alta gets a lot of snow. And we could also compute the median with np.median. We get a median of 90.85. Any thoughts as to why the median is so much higher than the mean for this data? We had a mean about 80 and median about 90. Oh, what's that?
Like a lot of the points in the data were higher up, so that there was not a lot of small, like lower end.
What's that?
It's just what you were saying, like the value of October seems to be much lower than most other values.
Right. And what do we call a value that's a lot lower than all the other values? An outlier, right? Very good. So we have this outlier. October is actually an outlier compared to the other months. It's so much smaller than all the other months. So we have an outlier at the bottom of the data set, and that is making the mean. It's kind of pulling down the mean. You can think of the outliers kind of pulling the mean towards them. And so that's because indeed the mean is quite affected by the outliers, but the median isn't. Okay, I have a question in the chat. Let me just, Okay, not a question and answer. Okay, thank you. Okay, so let's see now how we can make a plot of this data with the matplotlib library. So I'm going to start off with not a lot of code so that you can kind of see what each line does, because for me, that's most helpful in parsing through all this. So let me first run this and let's see what this does. So I'm calling the plot function. And so this plot function, you can just plot an array and it will create some kind of default X values to plot it against. Or more generally, you do plot X comma Y, and that's going to make a plot of X on the X axis and Y on the Y axis, as you would expect. Okay, so what am I doing here? First, I'm creating my X values for the plot. And this is with the np.arrange command. Let's take a look at, actually, let me move this up here and print this before the plot so you can see what this is doing. Okay. Okay, so this np arrange 7 is just creating an array, 0 through 6. Last lecture, we looked at the range function, right? And that is very similar to this function. The range function is just a built-in Python function, whereas this arange function is like the equivalent function in the NumPy package. So you can use either. All right, so we're getting this plot. We've got this 0 through 6 on the bottom, and then it's making a plot of X versus Y. And then if I added this little comma O, that would turn it into a scatter plot. And so you can see that's what it would look like. If I plotted it with that extra input, I'd get a scatter plot instead of a line plot. And after every plot I want to display, I have to do plt.show. If I don't do that, it's not going to display the plot. So after every plot you want to display, you have to do plt.show. Okay, so let's see, what's all this other stuff? Well, this line is going to label the X tick marks with the strings appearing in the months list. So you can see that changed my 0 through 6 to October through April there at the bottom. This next line is going to add just a straight line across the plot where the mean hits. How is this doing this? Well, it's just actually saying it's giving Python 2 points, the point 080 and the point 680, and it's just making a straight line connecting those 2 points, and it's giving it a label. And I can do the same thing for the median. Okay, that's going to be the purple line, and I can give my plot a title, and I can give my x-axis a label called month. There we go. I can give my y-axis a label called snowfall in inches. And I can also make a legend, which I'm going to put down here. And if I'd labeled the red curve when I plotted it, it would also show up in the legend. So whatever you label will show up in the legend.
Can we use range for this as against a range?
Yes, you could. So that should be fine. So let's try that, right? If we just use range instead.
Okay, MP goes
up. Yeah, so I think that that's fine. I don't think that that's going to cause any issues. I could be wrong about that. You might want to double check. But I don't, that like inside the plot function that it's expecting the NumPy formatting, it's possible. Okay. I'll just put it back to be safe. Okay. Yeah.
So for the lead, like the PLT plot, means no, you have a lead with less level.
Do you mean this part right here?
Yeah, yeah.
Yeah, so it's not, that is a list of 2 and 2, but it's plotting it on the same plot window because we only have one, we don't say plt.show until down there, which means it's going to take all of those plots and plot them on the same window. But if I did this, for example, if I did this up here, and then I did that, notice when it plots this on its own, I didn't think it would, oh yeah, well, I labeled it 0, 6, but yeah, but this is still, it's just plotting based on 2 points, which is a value here and a value there. So it's just plotting 2 points and connecting them, but it's putting it all on the same axis.
The length of this is just
Yeah, yeah.
What's the x-ticks? The last one?
What does the x-ticks mean?
Yeah.
It means the values here along the bottom. So these are the x-ticks are like the x increments, the increments along the x-axis. And this is just saying to label, to use the months array to make those marks. Does that make sense? Yeah. Otherwise, we just see 0, 1, 2 through 6 on the bottom instead of the actual names of the months. Yeah.
Still the question of line. So it's just like a matrix with the first row is 0, 6, and the second row is no. So we have that.
Yeah, more generally, you could think of it as first of like you're making like a plot, and first you put your a list of your x values, and second you put a list of your y values. That's really all we're doing in both cases. Yeah, so first list of x values, then list of y values. Any other questions? Yeah.
So I'm seeing that note over there that you can just use plot and then 1 parameter, and you'll just use like 1 to whatever as the x.
That's
So
right.
does that mean we don't actually need int.range?
So in this case, we wouldn't if we were okay with it just plotting like 0 through 6 on the bottom. But if we want to relabel it, do we have to? I don't know, since we're relabeling it with the months names. In this case, I think it would be fine. For example, if we took this out, and let me take out this from what I did before. In this case, it would be fine, but that's also because like what we're using here is the default of what it's plotting against. You know, it is 0, 1 through 6. Yeah. Other questions? Okay, so it's kind of a lot when you first start doing it, like getting used to all of the syntax here. But once you get the hang of it, you'll start to kind of do the same things over and over again. So that's how we make a basic plot. That was looking at a tiny data set. Let's look at a data set that's a little bit bigger. This is population data from the 1994 census. And here is where we're going to use pandas to import the data. So let me run this. And so this is using pandas to read the data from this website and specifically to pull out these different variables. And this is comma separated data. We'll discuss that in more detail next week. So I'm not really going to go into this yet. That we'll talk about next week. But for now, just know this is a pandas data frame that we've created. And if I print it, I can take a look at what this data frame looks like. Okay, this is just kind of, this first column is just telling me what my different entries are, row 0, row 1, row 2. And then I have all of my variables showing up as columns, and I can see what some of the different variables are: age, employer, education, etc. Okay, so now if I want to do some descriptive statistics, one easy thing that I can do is I can just pick out a column and I can make it a list. So if I look at the data frame and I look at the age column, I can do .toList, and it's just going to make a list which I'm calling ages. And that is going to be a very simple object, which is just a list of numbers. So that's one easy way to extract. If you just want, you know, if you're just interested in a couple of things, you can extract them as lists. Okay. Okay, and then here, let's say we're interested in some descriptive statistics, like the length of that array, the min, the max, the mean, the median. We can compute all of that. So this is a pretty big data set, right? We have over 32,000 entries. That's the length of the list. The minimum, this is on income data. So it's people who are reporting income. The minimum age was 17. The maximum age was 90. That kind of makes sense, right? We have people between 17 and 90 reporting income data. The mean age being 38.5 and a median of 37. Okay, so descriptive statistics are nice, but they don't tell you everything. A lot of time, they don't really tell you everything about the shape of the data, the distribution of the data. Do you see like multiple peaks in the data, etc. So a lot of times we want to get a picture of the data because that's really more descriptive. And histograms are kind of the most basic tool to use to do that. So let's make a histogram of this data. So the function is .hist. So I'm using this PLT library .hist, and I'm making a histogram of the ages list. And here I can tell it the bins that I want to use in making the histogram. Actually, maybe first of all, let me just do this, the default, make a histogram of ages, and we can see what that looks like. Okay, I think it defaults to, I don't think that was 20 bins. I'm not sure how many bins this is. Whatever the default is, doesn't look like 20 to me, sorry about that. But if we want more control, we can actually tell it what bins to use. And here we're having a little bit more granular bins, which is nice. We can get a better idea of the shape. And then we can add a title and a label for our x-axis and our y-axis, just like we did before. And we have to do plt.show to see the picture. So what you can kind of see a bit of a, we're not really going to go into this a whole lot, but it looks like there's a bit of a right tail, right? It's like skewed in one direction. Okay, so another quite informative descriptive statistic is something called quantiles or percentiles. You can call them percentiles, and you can compute them with this np.percentile function. So this is asking for the 25th percentile and 75th percentile in this distribution. So what does that mean? It means, well, first let me run this. Okay, 25th percentile is 28 and 48 is the 75th percentile. So that means that in this data set, 25% of the individuals are under 28. The middle 50% of people are between 28 and 48. And the oldest 25% of the people are older than 48. Does that make sense? Yeah, we got a question?
Yeah, so when you're talking about this, all you were talking about is just like the width of each of these boxes in this.
Oh, when I'm talking about the bins up here.
Yeah, and as you increase the density, get narrower.
So what you put in here is a list. Actually, let's print this because that will be probably a little bit more informative. So if I print this, let's see what this looks like. Okay, so this is what's being input into the function, this list, 0, 4, 8, 12, etc. And so then what the histogram is going to do, it's going to say, how many observations do I have between 0 and 4? It'll plot that. How many observations do I have between 4 and 8? Plot that, etc.
And as you increase the base, it's small.
Exactly. So as you make the bins more granular, like you make this list longer, they'll get narrower, right? And so, for example, if I change this to go every 2 instead of every 4, we'll see more granularity there. And you notice how now it's a little bit finer, but also a little bit noisier. So there's kind of a balance here. You want the bins like small enough so that you can really see the shape, because if I don't use enough bins, let's say I do like 10 here, then it's kind of hard to see the shape. But if you use too many, you're going to see a bunch of like spikes up and down. It'll look a little noisy. So you kind of want to see the shape, but you want it to be smooth. A little bit of an art. Okay. Okay, so right, so we were talking about the percentiles and what that means. And how do I read off quantiles from a histogram? So what you would be looking at, let's say we looked at this histogram and we want to just kind of do a ballpark estimate of what the median is. We're looking for the point where we have 50% of the area less than that point and 50% of the area more than that point. So you can kind of see, yeah, like somewhere about like right here, somewhere around 50, a little less than 50 probably, 45 to 50. You got half of the area to the left and half of the area to the right. And that's what we see. The median was like 48. No, it wasn't. Hold on. What was the median for this? Oh, the median was 37. So that's actually over here. Yeah, I guess if I had looked at this plot, I would have guessed it to be a little bit higher. It's a little bit hard to read off the areas sometimes visually on the plot, but you kind of get the rough idea. It might be helpful if I use more bends, right? Go back to the, oh, we had just computed that. Up here. We had asked for the median. Yeah, so we'd seen that that was 37. So what that should say is that when we look at this histogram, if we find 37 and 37 is going to be like right here, right? Okay, somewhere right there, that half of the area is below it and half of the area is above it. And that is indeed about true. It's just sometimes a little bit hard to tell when it's skewed like that, how much area is stacking up. Okay. Okay. Any other questions? Okay. So one thing that these quartiles will tell you, for example, if the first quartile or the 25th percentile is much, much smaller than the third quartile or the 75th percentile, that means you have kind of a broad range of values in your data set. But another way that you can characterize how much dispersion or how spread out the values are is by something called the variance or the standard deviation. Okay, so this quantifies the amount of variation or dispersion in a data set. And yeah, we talked about the mean, which is just add up all the values and divide by the total number. What the variance does, this is also a mean, but it's a mean of, take each value in the data set, center it, so subtract the mean, then square it, and then look at the average. So it's the average squared deviation from the mean. And you should think about what does that mean? Well, if I take the square root of that quantity, I get what's called the standard deviation. And in some sense, that's like the typical amount of deviation from the mean in the data set. Okay, so if I compute this here, I'm going to get a variance of 186 and a standard deviation of 13.6. The nice thing about standard deviation is it has the same units as the original data. So I can say that there's a standard deviation of 13.6 years for this data. And in terms of how this is going to be related to a plot, to a histogram, if I have a small standard deviation, that means most of my values are really close to the mean, and I'm going to get kind of like a tall, narrow histogram. If I have a large standard deviation, that's telling me that my data is really spread out, that I have a lot of data far away from the mean because the average squared deviation is high. Okay, so a large standard deviation is like a really wide histogram. Okay. Yeah.
That's a sample or population.
Oh, good question. So what I put here is what we would call the population variance. If you,
I mean, for the Python.
for the,
For Python, is that the sample or population?
that is an excellent question,
Yeah.
and I don't remember. Let me check on that and I can get back to you. Normally it's the sample. So normally, in fact, if you ask a computer to compute the variance, it'll put an n-1 there instead of an n, because that's what's called the sample variance and standard deviation. And I need to double check now if it's.
This is the sample variance we need to put by ourselves instead of.
No, you don't need to worry about it. In practice, there will be not much of a difference between using n or n-1. I'll try to double check that at the break. Okay, so I think we just wrote it this way up here so that you can sort of, to give the intuition that it's like an average squared deviation. And this is kind of a minor statistical point that in practice, you usually use an n-1 instead of an n when you compute it. Okay, other questions? Okay, great. Okay, so let me see how I'm doing on time. I guess we should take a little break if we're going to do it. This is a good stopping point. So why don't I take a little 5-minute break and we'll come back at 4:23. Okay.
I have a quick question in the interim. Can anyone hear me?
Okay, according to the internet, it looks like it is the population standard deviation that it computes.
Can you show me how to do the git pull? Yeah, I'm not sure how to get into the directory.
Have you cloned it to start with?
Yeah, I did.
And where is it?
I'm not sure.
So we need to know where it is on your, or we can just start over if you want.
Yeah, sure, sure.
If you, oh. You mean for the lectures?
Yeah.
Okay, it looks like, is that just in your home directory?
Maybe. Yeah.
Okay.
I just cloned it there.
Okay, so if you actually go to a terminal, okay, and let's just check. Let's see if we see it in there. We do, we see it in there, right? So you have a directory, which is the 2022 Data Science Lectures. Navigate in there. So do a CD followed by the name of that. So CD, you want to leave a space, actually. And then 2022, now you can do a tab to try to autocomplete. Okay, now lectures, there you go. Okay. Okay. Do a git pull. And now it's updating. So now you should have the new files in there. You're welcome. Yeah.
So when I was going to turn it over, I noticed it wanted a zip file. Do you just want me to just zip the iFile?
Yes, it's just better that way to not be too large for uploading to Canvas. Yes. No problem. Okay, let me see. I have a couple of questions in the chat that I'm just now seeing. Let me go through them now. How large can our groups be? So this was Wayne's question. You mean the groups for the group project, correct?
Yes, yep, exactly. Yes,
Okay,
can you hear me?
He might be on break. But for the group project, it should be a group size of 2 to 3 people. I think 4 people. Okay, somebody, am I muted? I'm not muted in Zoom. Can everybody?
You're not muted, but Wayne
okay?
was talking. Can you hear us?
I can hear them like slightly.
Okay, how do I? Media volume? What's this? Can you say something now?
Can you hear us?
Oh, there we go.
Yeah, can you hear me?
Now I can hear you. I had the, yeah, okay, I think I got it now. Go ahead.
Oh, I was just asking about the group sizes, if 4 was too many.
It's a little large, yeah. I would say
Okay.
2 to 3 is probably is probably better.
2 to 3, okay.
Yeah.
Thank you.
Yeah, it's just kind of a lot to coordinate. Okay, let's see what other questions. Now we fix the audio, good. Okay, great. I think most of that was about not being able to hear. Okay, great.
So I'm just confused on what it means to like do the recursive function, but not copy the list. So like the other version of our recursive function, not copying the list. Like what exactly is that?
Okay, so let's see. Actually, do you mind if we take a look after class?
Yeah, sorry, I thought it might be a little long.
No, it's okay. And honestly, I need to refresh on what those problems are.
Okay.
So maybe we can discuss after. Okay. Yeah, you're welcome. Oh no, other people have the same question though. Yes, I can keep the Zoom open for that. Absolutely. I will just apologize ahead of time that I have not had a whole lot of time to look at the homework, right, for this week, because my kids got sent home from school for distance learning. Okay. Okay, so let's get started again. Okay, everybody ready? You guys are so engaged. Okay, but let's come back together. So what we've been talking about so far is looking at one variable at a time, right? We just have one variable, we're looking at all the values and we're doing some descriptive statistics of that variable. But in practice, we're interested in having multiple variables and knowing how they're related to each other. Do they, what kind of relationship or impact are they having on each other? So one thing that you can do is you can look at the covariance or the correlation between two variables. So the covariance of two variables, X and Y, is given according to that formula. Okay, again, it's an average. We are looking at the average of X minus its mean times Y minus its mean. So mu X is the mean of your X values and mu Y is the mean of the Y values. And if you take that covariance between the two variables and you normalize it by standard deviation of X times standard deviation of Y, you get what's called the correlation between X and Y. And so this will always be on a scale ranging from -1 to 1. So that's what's nice about the correlation. Okay. Right, sigma X standard deviation of X, sigma Y standard deviation of Y. So take a look at some of these plots. Okay, if we have this right here, what we see is there's like a perfect positive correlation between X and Y, and we're going to get a correlation of 1. Here we see a strong positive correlation between X and Y. We get a correlation of 0.8. Here we see a weak positive correlation. Here we see no correlation whatsoever. Here we see a weak negative correlation, a strong negative correlation, and then finally a perfect negative correlation. So these correlation values range from -1 to 1, and the closer they are to 1 or -1, the stronger the linear pattern is in the data. Notice the slope of the line doesn't really matter, right? So for all of these different patterns or lines, we get a correlation of 1 and -1, regardless of the slope. But you should also be a little bit careful when you're looking at correlation to know that it's checking for a linear relationship between the variables. And it's possible that there is a significant relationship between the variables, but that it is nonlinear. For example, if you look at this first little plot of X versus Y values, there's clearly a strong relationship between the values because you see this W pattern emerging. But if you looked at the correlation, it would be 0 because in a sense, the regions of negative correlation cancel out with the regions of positive correlation. So you have to be a little bit careful about that. A low correlation doesn't mean there's no significant relationship. It just means there's not a significant linear relationship. Okay, same like with the circle over here. Clearly a strong pattern, but not linear. Okay, so let's take a look at the correlation between age and hours worked per week in this census data. So I'm going to make another list, just like I did before, with number of hours worked per week. And then this is kind of a cool function. It's hist2d. It's going to make a two-dimensional histogram based on these two variables using 25 bins and give me some titles. So let me do this and let's take a look. This is the two-dimensional histogram that I get. So I know we don't really have like a scale here for these colors, but but yellow is like really high values and blue is really small values. So what do you see in this data? You're right that most of these high values are, 30 to 40. But what if you look this direction? Yeah, just like everybody's working 40 hours a week, right? So that's what we see. We see almost all of the data is right here at 40 hours a week because most people are working 40 hours a week. Yeah.
So like the colors, that's like the number of people that are working within the data set.
That's right. So
Okay.
think of this as, okay, you have like our X and our Y. The color is corresponding to the height. So this is a two-dimensional plot. So the bright color is like a tall value and the blue color is like a really short value. So we're seeing that all of the data is right here, or not all of it, but most of it is right there. And that's because most people, sorry for my Zoom people, I stepped away, are working 40 hours a week. I mean, you do see, like if you notice, okay, we have a little bit of action up here. And we do see the people who are working crazy hours are under 50, right? The old people are not doing that. And we also see the people who are working like 10 hours a week or teenagers. But overall, what would you say? Do you think there's much of a correlation between age and hours worked per week? Yeah, I'm seeing a no. There's not much of a correlation because everybody's working 40 hours a week. And we can get like a scatter plot also. If we look here, this is getting a little scatter plot, ages versus hours. And the scatter plot is a little uninformative because what we don't see is we don't see that height that we see in the other plot. We can't really tell that so many of the values are just plotting on top of each other at 40. So I kind of like the first plot a little better for visualizing, but we do see a lot of scatter. So let's take a look at the correlation coefficient. So we call this function core coef, ages hours. And it's going to return a little matrix because we could call it actually with 3 or 5 or 10 variables, and it'll show us the correlation between each pair. But for 2 variables, it's just going to be a 2x2 matrix. What this one up here means is that's just the correlation of ages with itself. That's always perfect. So that's 1. This is the correlation of hours with itself. That's just 1. Correlation of anything with itself is 1. But this is what we're interested in. This off-diagonal value is telling us the correlation between ages and hours, 0.06. Okay, that's very low, right? So that's a very weak correlation between the variables. Okay, and then got another question in the chat. Okay, I think that's about the recursion stuff. So we'll maybe come back to that after class. Okay, one thing to keep in mind when you're looking at correlation is the difference between correlation and causation. So just because 2 variables are strongly correlated does not mean that one of them is causing the other one. This is a fun little graphic that gets at this fact. I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. Right. Who knows what's, so they're correlated, but who knows if that's the cause. If you go digging, you can find all kinds of weird correlations. So check out this website if you're curious. But here's just 2 examples, a couple of examples. If you look at per capita cheese consumption, and you look at the number of people who died by becoming tangled in their bed sheets, you see a really close correlation, right? These trends tend to match each other pretty closely. Okay, so stop eating that so much cheese. if you look at total revenue generated by arcades and computer science doctorates awarded in the US, again, you see this sort of close tracking of arcade revenue and CS PhDs. Okay, so we observe a lot of times strong correlations between variables that we know can't be directly affecting each other. And what's usually going on in that case is something called a confounding variable, right? There's a third variable that's affecting both of them. So for example, let's say we are given some data from the city for a 4-month summer period. And let's say we analyze this data and we observe that swimming pool deaths tend to increase on days when more ice cream is sold. So should we tell everybody to stop eating ice cream? No, yes, indeed. So what might be the confounding variable in that example? Temperature, right. So the hotter it is, the more people go to the pool. The more people go to the pool, the more people might potentially drown, but also the more people eat ice cream. So indeed, this temperature is a confounding variable. Okay, so this is, not a difficult concept, but it's very important, and it's very difficult. I mean, unfortunately, in most scientific studies, what we really want to say is say something about causation, but that's very difficult to do, because to do that, you need a highly controlled, randomized experiment, and most of the data that we have is not a highly controlled, randomized experiment. So we just have to be careful in our interpretations. There are ways that you can try to control for confounding variables by putting them directly into the model. That helps, right? If we put temperature into the model, we may see, oh yeah, ice cream doesn't have anything to do with it. And we'll talk a little bit more about sort of choosing variables when we do regression methods in the future. But for now, just be careful that you don't say, X is causing Y when they're just correlated. All right, we are going to skip this little activity for now and see if we have time for it at the end of class. Sorry about that. I feel like I always go slower than I mean to go, but I want to make sure that we kind of get through this material that you're going to need. Okay, so now we've spent a good bit of time talking about descriptive statistics for quantitative variable and about exploring the relationship between two. Another important concept is inferential statistics. So descriptive statistics quantify or describe features of a data set. But in inferential statistics, we're viewing the data as a sample from some population. And what we really want to know is we really want to know what's true in the population itself. We want to make inferences about the population. So for example, you can think about in an election year, we want to know what's going to happen in the election. We want to know who's going to be elected, but we can't take a survey and survey everybody in the country. So what do? We take a sample and we take, so we get some survey, some sample from the population, ask them how they're going to vote. And then we try from that data to infer what we think is true in the population. But there's randomness involved, right? And the inferences we make may not be perfect, but that's the goal, is from a sample of data from a population, we want to infer, we want to learn something about the population itself. And so often we'll model a population characteristic as a probability distribution. So we're observing some variable, and like we were seeing with the plots of the histograms, it takes on different values with different probabilities. So we model it as a probability distribution. And then inferential statistics is all about deducing properties of that probability distribution. For example, what's its mean? What's its variance? Some basic things like that. Okay, So in the time that we have left, we're going to go over a couple of famous distributions that will be helpful, and a little bit also about how we characterize probability distributions. So first of all is the Bernoulli distribution. This is the easiest one, okay? A Bernoulli is just a yes or no. It's like the flip of a coin, heads or tails, but we make it a number. We make it 1 with probability P and 0 with probability Q or 1 minus P, okay? But just think of this as your basic coin flip. Okay, so there's just one parameter determining this distribution, which is the probability that you get a 1. Now we can sample from this distribution using Python. So we're going to import the SciPy library as SC, and then we're also going to import from SciPy.stats Bernoulli binom, short for binomial, and norm, short for normal. Go ahead and do that. Okay, so with these functions, we can do simulations. So we can simulate a random variable with this distribution. So let's say we make a variable n, which is 1,000, and then we simulate some coin flips. And how do we do that? Well, we call the Bernoulli.rvs function. .rvs basically means draw random values from this distribution. So draw random values from the Bernoulli distribution with Bernoulli with a parameter p of 1/2 for a fair coin toss. And how many of them are we going to do? We're going to do 1,000 draws. And so if I print this, I should see a list that's 1,000 elements long. Each one of these was a coin flip, 0 or 1. What do we notice? About half zeros, about half ones, right? So this is what's going on here. So let's see exactly how many ones we get. Here, if I sum that list, I'll get how many ones I have. And then if I take that sum and I divide by n, I'll get the percent of ones I have. Okay, so I got 488 ones, which is 48.8% ones. Okay, and so you can see here, this is kind of random. It's not kind of random, it is random. If I do this again, let me do it again, you're going to get a different answer. Right? Okay, now we got 49.5%. And I could keep doing this. Now, so we're kind of, let me do it one more time. Just for fun. Okay, let's see what I get now. Ooh, okay, now I get like 50.1%. So we're seeing a bit of variation here. Now, what's going to happen if I, instead of doing 1,000 coin tosses, I do, how many am I doing here? 1 million? I think I'm doing 1 million coin tosses. Any guesses? Yeah, exactly. It's going to get closer to 50% the more we do. So we would expect, so notice this is like 0.4999, right? It's so the more we do, the closer it's going to get to 50%, which we refer to in statistics as the law of large numbers. Okay, but things to remember about the Bernoulli variable. If we're just looking at one little coin toss at a time, the mean of that variable is p, and the variance is p times 1 minus p. Yeah.
I don't understand quite what variance like is supposed to tell us. So I know standard deviation is like the average point for each data point. Of the data existed of each data point, but variance, like what exactly?
Well, the variance is the square of that. So they're closely related, right? If we go back up here to this definition, let's see, where did we talk about this? Yeah, in this case, the variance, it's like the average squared deviation, but you always compute the standard deviation by first computing the variance, which is a little less intuitive than the standard deviation. But if we think about, if we have the coin toss, what is the mean? Well, the mean is, for my Bernoulli, it's going to be 0. Sorry, it's going to be 1 with probability P, and it's going to be 0 with probability 1 minus P. And that means that the mean is going to become P. So then if I think about the variance, I can work out why it has to come out that way, but it's just based on 2 values, because you have 2 different values and different probabilities that they occur. Granted, we haven't really gone into, how to do those calculations. Yeah. Does that help at all? I know it's.
Yeah, it does.
But okay, maybe a little bit more of an intuitive explanation would be.
It does help because you said that in order to find standard deviation, you have to find the variance. Which makes
Yes,
sense.
that's right.
So standard deviation is the intuitive one, and like you have to understand the variance.
Yes. And so you could think, when is the variance the largest and when is the variance the smallest, right? So if we have a P of a half, we're going to get a half times a half, which is a fourth. On the other hand, if we have a very unfair coin, a P close to 0 or a P close to 1, the variance is going to be a lot smaller. So one way to think about this is, the variation is going to be the largest when we have a P close to a half, and we'll get small as we take small p's. Okay, but usually, so that it's interesting to look at the Bernoulli distribution, but usually what we're more interested in, hold on, before I do that, let me see if there are any questions. Okay, I'm just coming back to the Zoom. I'm sorry if I missed something important. Feel free to interrupt me and ask a question if it's something related to what I'm talking about and I don't see it. So I don't think what was in here was related, but please interrupt me on Zoom if you have a question. Okay, usually what we're interested in is not just each individual coin flip, but what we were doing before, where we were aggregating, right? We were doing like 1,000 or 1,000,000 and seeing what percentage heads we got. And so that's what is described by the binomial distribution. The binomial distribution is described by 2 parameters, n and p. So p is the probability that you get a 1 when you do a Bernoulli coin toss. But let's say we do n coin tosses, and then we count how many came up heads. Then we count how many we have. So it's like summing up all of these Bernoullis. We're going to do n Bernoullis, we're going to add them all together, and we're going to say, in the total n trials, how many successes did we have? And that is called a binomial distribution. Okay, so let's once again consider a fair coin underlying the experiment, so a P of 0.5. And then for each flip, the probability of heads is P. And we want to keep track of how many total heads we have in the n experiments. Okay, so let's see how we might do this in Python. So first we can set P to be 0.5. And let's say we're going to do n trials. So we're going to think about tossing this coin 10 times. Then I can call the binom.rvs function. So that's going to say, draw a random value from the binomial distribution, where the binomial distribution is with parameters n and p. And then this last input is just saying, I want to sample a bunch of different values from this distribution. So do this, 1,000,000 times. And let's see what we get. Okay, so we can see a bunch of different samples from this binomial distribution. Most of them, right? I guess if you had a fair coin and you tossed it 10 times on average, how many heads would you get? 5, and that's in line with the data that you're observing here, right? So we're getting 5-ish, but of course there's a range, and we're seeing all these different values. Okay, let's make a little histogram of these values. So first I can define the bins I want to use for my histogram. I'll print that out so that you can see more specifically. Okay, these are the bins. I'm going from, my possible values are 0, 1 through 10. So I've made for my bins, starting from minus 0.5 to 0.5, because I want each integer to hit in the middle of the bin, right? That's one way that I can do it. So this, first I'm going to count how many zeros I have, then I'm going to count how many ones I have, then I'm going to count how many 2s I have. And if I look at this plot, now I'm going to do my plt.hist of these binomial variables. I see this little shape right here. What do I see? It's centered at 5, as we expected it to be, and it's symmetric. Okay, so for this distribution, we have a mean of n times p. That actually makes sense. We're just adding together n of those Bernoullis. And we have a variance of n times p times 1 minus p. In this case, the variance also just adds together because these things are assumed to be independent. We're assuming that what happens in one coin toss doesn't affect the next one. Okay. And so I can describe a distribution in a couple of ways. And usually we have a different way of doing it for discrete variables and for continuous variables. When I have a discrete random variable, I describe its probabilities with a probability mass function. And that just tells me what are the different possible values that this thing can take on. Like before, it was 0, 1, 2, up through 10. And what probability does each value occur? So for the Bernoulli, the probability mass function would just be this guy right here. All this is saying is that I'm going to equal 1 with probability p, and I'm going to equal 0 with probability 1 minus p. That's the probability mass function. For a binomial random variable, we have more different values, right? And the probability mass function is described by this thing right here. The probability that I am equal to k is n choose k times p raised to the k, 1 minus p to the n minus k. And here, k is going to range from 0, 1, 2, up through n. Okay, so this is a little, don't worry about that. It's defined in terms of factorials. If you've seen that before, great. If not, no big deal. It's just the probability that you get out. Okay, so let's see. We can access this in Python as follows. First of all, we'll do this also a little bit more later in the class. In this first line, I'm defining a function. It's called a lambda function. It's kind of like a shorthand way to define a function. But what this is saying is f is a function that is going to map k to the binomial PDF evaluated at k, and these are the input parameters for that binomial. So here I'm just defining a function, which is the binomial PDF. Then I'm creating an array of x values, and I'm going to plot those x values, and I'm going to plot the function evaluated at those values. So I'm plotting this probability mass function of the binomial. And let's take a look. Okay. And so what do you notice here? Again, it's centered at 5. It's taking on the same range. It looks a lot like the histogram that we made. Okay. And that's the whole idea, is that if you take a large sample of a variable and you make a histogram, it's going to be a very good approximation of the underlying probability distribution of the variable, right? So here, this is the true underlying probability distribution. The histogram is what we would approximate by collecting data, but they're going to be very close if we take a large sample size. Okay. Okay, so let me just see, since I only have 5 minutes, let me see what is the most important. This is just a little recap, so you can read that. And let me talk a little bit about, normal distributions and continuous random variables in general. So another really important distribution, probably the most important distribution, is the normal or the Gaussian distribution, famously described as a bell curve. This distribution is governed by 2 parameters. The first is mu, or the mean of the distribution. The second is sigma, or the standard deviation of the distribution. And so here, what we're going to do is, first of all, define the mean and standard deviation, and then just create a list that ranges from mean minus 4 standard deviations to mean plus 4 standard deviations. And then we're going to evaluate the PDF of a normal distribution on that list. So let's take a look at what we get here. This is the famous bell-shaped curve. Okay, so we've just made a list that goes from minus 4 to 4, and then we've evaluated what's known as the PDF, or the probability density function of that distribution. You may be scratching your head a little bit as to what is this function, which is a great question. So what do we mean by this? What do we mean by a probability density function? Okay, so this is where there's a difference between discrete and continuous random variables. Discrete random variables have their probabilities described by some discrete function, probability mass function. Continuous random variables in general have their probabilities described by some continuous function defined everywhere. So for a normal distribution, the PDF has an explicit formula, which if you plot it, will show you a little bell shape. But what is the idea? How do you get underlying probabilities from this function? Well, the idea is that if you take this PDF function and you integrate it from A to B, it's going to tell you the probability that your random variable takes on a value in between A and B. Okay, so if you think in terms of population, if you pick somebody at random from the population and you want to know the probability that their value is between A and B, it's given by integrating this function. Okay, so what we did. Okay, right. So for example, if we wanted to calculate the probability of being within 1 standard deviation of the mean, we would use an A of mu minus sigma and a B of mu plus sigma, and that would give us the corresponding probability. So let's try this right here. We're gonna make that plot once again, just like we did before, and then we can also make a second plot on top, which uses a new list going just from 1 standard deviation, mu minus 1 standard deviation, to mu plus 2 standard deviation, and fill in this area in between that and the PDF values. Okay, this alpha parameter controls transparency. So if I lower this, you'll notice the plot becomes more transparent.
What's the value of that? So that's the area of the integration.
Okay, so we're gonna have to figure that out, right? So let's see. Let me have you guys guess. So what we have right here, let me put it back to 0.5. So I've just highlighted here the area corresponding to 1 standard deviation below the mean to 1 standard deviation above the mean. What percentage of the total area do you think that is? I think you guys had had a statistics class, because that's remarkably precise. Indeed, this is 68, it's about 2/3 of the area, right? So this is about 68%. Now, if we didn't know that, or if it's not like a standard one that we've memorized, how do we figure that out? Well, the basic idea is that the total integral has to integrate to 1 because these are probabilities. So we have to be, probability of being between minus infinity and infinity is 1. So this total area under the curve is 1. The function integrates to 1. And so then we can calculate these values with a closely related function called the cumulative distribution function. So the cumulative distribution function is usually written with a capital F, and it's just defined as the probability. So capital F of X is the probability of being less than or equal to X. And so it's the integral of the PDF from negative infinity up to X. And then it's easy to see that if we want to calculate this value right here, which is the probability of being between A and B, we take the CDF evaluated at B and we subtract the CDF evaluated at A. Okay, so we can do that for this normal distribution. We're going to take the CDF evaluated at mean plus 1 standard deviation, and we're going to subtract the CDF evaluated at mean minus 1 standard deviation. And let's see, indeed, we get 0.6826. Okay, so that's basically telling us that the area here of this red region is 0.68. Okay, now could you have done this on scratch paper? Probably not, because that CDF function is not any kind of easy way to evaluate that. So generally, you have to use technology or some kind of lookup table to actually evaluate that function. Okay, and I'm 1 minute over. I think, though, I actually got through most of the important stuff. Let me see if there's anything else. Yeah, I think we covered this. So, right, so to evaluate these probabilities, CDF at the upper minus CDF at the lower, and you can see exactly how to do this in the code. And then if we run this little part, we'll just sample from a normal distribution and make a plot. And once again, you'll see that the histogram really closely approximates that underlying PDF function. Okay, so when you have a large sample size, the histogram is going to approximate the true probabilities. Okay, so let me call it a day there. Any questions? Okay, great. Well, you guys have a lovely rest of your day, and we'll see you on next week, right? Today's Thursday. It's been such a whirlwind of a week. Okay.
I just have a question about this one.
Yeah, sure.
So even in class, we don't get to do activities, we get to do activities on here.
Yeah, so throughout the semester, you just need to do 5. So you don't have to do all of them. And you can kind of upload any of them to any of them, if that makes sense.
Okay, yeah.
As long as you upload, 5 activities by the end of the semester.
So when I upload it, do I upload it in here?
Yes. Mhm.
Same
And
with
you
the
just zip
assignment,
it, just like you do for the homework. Just zip your Jupyter notebook and upload it there. The only thing is the activities, we're just checking that you did it. We're not like actually grading them for correctness. The homeworks, though, of course, will be, closely checked for correctness.
And my next question is same thing with the homework. So how would I zip? I'm not done, but I'm just wondering how I would submit it.
Okay, so if you go to like your Finder or, yeah, and if you navigate there into wherever it is.
Good luck with that. I was trying that last time, but when I use git pull and Jupyter notebooks and stuff like that with the command prompt, it doesn't save like a local version onto my computer as far as I'm concerned, because I tried it so many times. I tried it normally.
Yeah.
That was last time. His last class, I saved it. The TA was helping with that. Yeah, when I use git pull to extract it and put it on there, is it saving somewhere on my local computer, on my local
Yes.
drive?
Yes.
Huh. Well,
Yeah, it should be somewhere there. If you just kind of opened it up, it might be in your home directory,
let's see, if I'm on here,
Yeah, go back to where you opened this from.
yeah.
It looks like you're just in your home directory.
No, it's just, so like my OneDrive, so I should have a home directory file called 2020 data science homework, right?
Yes, I think so.
Sure where it goes when you do the get poll.
Yeah.
Okay, I have a Windows too.
Oh,
and
yeah,
so,
look at you, you're actually
yeah.
Great.
So I have like,
Yeah.
so
Oh, thank you for the reminder. Let me do that.
cool.
yeah.
Okay.
Yeah, and then